So welcome all for the lecture series on advanced computer architecture series. This is module number 3 and lecture number 25. So in the last class we have studied about shared memory organizations. In shared memory organizations we have come across how these are organized. Then we are come across different cache memory organization. The first one is simple one, that is called as a sequential memory organization. In sequential memory organization, what will happen is all the memory locations are going to be stored one by one, sequentially, linearly, and this is the actual thing, uh, physical abstraction, how it is going to be stored. Okay, so just look at it. I will ask few questions based on this later. The difference between this and this is an abstract model. Just have a look. Sorry, it is automatically muted by mistake. Once again I need to start. So this is an abstract model and this is a physical model. In abstract model, we are going to divide it into two things. One is lower order bits and higher order bits. In higher order bits, what is going to happen is higher order bits are going to check which module it is, whereas lower order bits are going to be used for memory locations. This way we are going to save the traverse time. Whereas in the next case, consecutive word, the reverse of this, lower order bits are going to be stored for memory module addresses and higher order bits are for the location addresses. So we use interleaving. The advantage is whenever a processor requests data from the main memory, a block of data is transferred to the cache and then to the processor. So whenever a cache miss occurs, the data is to be fetched from the main memory, but main memory is relatively sorry again today lot of disturbances. Whenever a process requests the data from the main memory, a block of data is transferred to the cache and then to the processor. So whenever a cache miss occurs, the data is to be fetched from the main memory, but the main memory is relatively slower than the cache. So in order to improve the access time of the main memory, interleaving is required. We can access all four modules at the same time, thus achieving parallelism. From the earlier figure, you have shown that the data can be acquired from the module using the higher bits. This method uses memory effectively. Types of memory interleaving, we have checked the different types, how each one bit is going to be having transferring. Here there are different 8 modules of 4 MB each, and one bit is stored in each of this. So it is going to speed up the overall transfer process by 8 times compared to the traditional sequential memory accessing. This is about whatever we have discussed about in the last class. In this class, we are going to check about memory allocation schemes, memory consistency models. So memory allocation means how the memory is allocated. Suppose you are a provider and you, based on this, suppose you have a lot of land with you, and based on the request you are going to provide the land, and when the occupants or the process request is fulfilled, when he no more deserves the land, that is again reacquired. That is about memory allocation. Even though it appears to be very simple, what will happen is, if I go on allocating wherever I wish, then there are so many smaller pieces of land which are unused, that will create in underutilization of the memory. But if I strictly go on allocating, then I need to have a lot of complex housekeeping process. Again, that is going to be difficult. So we'll look at different kinds of memory allocation schemes. Then how to make this consistency, memory consistency. We will come across this and we'll check what is the difference between consistency and coherency. Memory allocation techniques are nothing but assigning blocks of memory on request to the processors. Main memory is divided into set of non-overlapping memory regions called as partitions that can be allocated in contiguous manner or non-contiguous manner. Continuous means serially, or non-contiguous means wherever required. The advantage of memory allocation techniques is simple and no hardware support is required, but there are some disadvantages like program size is fixed, wastage of CPU time, and memory not utilized fully, etc. There are two types of partitions as we have come across. The first one is a contiguous partition, which is divided into two categories, that is single partition and multiple partitions. Fixed, or again in multiple we have two kinds, fixed and variable partitions. Whereas in non-contiguous partition, which is again divided into three categories, paging, segmentation, and segmented paging schemes. In single contiguous Hello, Sri. Am I audible? Naveen? Sri Lakshmi? Vinaya?
Yes, sir, audible.
In the middle, feather cut has occurred.
Yes, sir.
Okay. Because I am experiencing some network issues over here. Okay, I will again start with where I have left. Then single contiguous allocation, it is the simplest allocation method used by MS-DOS. All memory is available to a process. Whereas in case of partitioned allocation, memory is divided into different blocks of partitions depending on the each process requirement that much is allocated. Whereas in paged memory management or non-contiguous allocation, memory is divided into fixed size units called page frames and are used in virtual memory environment. Whereas segmented memory management, memory is divided into different segments. A segment is a logical grouping of the processor's data or code. In this management, allocated memory doesn't have to be contiguous. In multiple partition allocation, user memory is divided into more than one partitions. There are two types of fixed partition or static partition and variable partition, or we can also call as dynamic partition. In fixed partition has equal or unequal size of partition, and the partition is allocated to an active process in the multi-programming environment. However, it may suffer from internal or external fragmentation. It supports only fixed number of active processes. So I will just show you what will happen in fixed partition. Suppose this is my memory, and if I am going to have, sorry for this one drawing, if this is 5 equal partitions I have made in the memory, this is process A, which needs only this much of memory. The remaining is unvested. Whereas process B needs until this utilizes. Again, it has taken more than one, again some is wasted. Whereas process C, it has only this. So the again this much area is going to be wasted. This is the drawback of fixed partition, because either you need to allocate the complete block or leave. That is the main problem with the fixed partition sizes, because it supports only fixed number of active processes. Whereas a variation partition has equal or unequal size partition, and these partitions are created dynamically. See here, when they are created dynamically, what will happen is, depending on the requirement, a block or hole is available in the memory or free partitions. Again, this is whatever we have discussed. We know that A, B, C, D. Suppose A needs only this much is area is allocated to A. The remaining can be used for B, and C may start from here to here to here. Then D may be inside it. The advantage is as and how it is going to be required, that we can allocate a block or whole of is available memory or free partition. Variable partition has no internal fragmentation, and it is better utilization of memory than fixed partition. However, variable partition suffers from external fragmentation, and it has overhead of compaction. Next, dynamic memory allocation algorithm. If more than one empty hole or blocks are available for an active process, then the operating system decides how to select a best hole or block using dynamic memory allocation. Until this, whatever we have discussed is about static memory algorithm. In dynamic, there are four different methods. First one is first fit, second one is best fit, third one is worst fit, and the fourth one is next fit. In first bit, what will does is it will start searching from one end to the other. It allocates the first hole that is big enough to process. They started from the beginning to search such empty hole. So first fit algorithm is simple to implement and faster to use. But it has going to be a drawback. Suppose if I need only 4 KB, if the first block I come across is 16 KB, then 4 KB block is allocated to me. Then in that 16 KB, 4 KB is used and remaining 12 KB is becomes unutilized. Whereas in the best fit, this allocates smallest hole that is big enough for processes. This is fast when all empty blocks or holes sorted in increasing order of size. Best fit minimizes internal fragmentation and it is actually have a very good efficiency and allocation. But the problem with best fit algorithm is that the search time takes the searching of the hole or block is going to take some amount of time and that is wasted. Whereas in the next one worst fit, this allocates largest hole that is empty for the process. This creates maximum internal fragmentation, but worst fit is a fast when all empty blocks are holes sorted in decreasing order of size. Next fit, this allocates first empty block or hole that big enough for process. Whereas next fit starts searching from where it has left from, not from the beginning. This is the difference between first fit and next fit algorithms. This works same as first fit algorithm. This is about the dynamic memory allocation. In dynamic memory allocation, we have four methods. One is first fit, second one is best fit, third one is worst fit, and the last one is next fit. Then the next technique we are going to talk about is memory swapping. Where swapping is a mechanism in which a process can be swapped temporarily out of main memory to secondary storage. That is when we no longer require a particular process's address locations for some amount of time, and again it will be taken to the main memory. So swapping is a mechanism in which a process can be swapped temporarily out of main memory to secondary storage and make that memory available to other processes. At some later point of time, the system swaps back the process from the secondary storage to main memory. Though performance is usually affected by swapping a process, but it helps in running multiple and big processes in parallel, and that is the reason swapping is also known as a technique for memory compaction. Where a process can be swapped temporarily out of main memory to a backing store and then brought back into memory for continued execution. Then what is backing store? It is a fast disk large enough to accommodate copies of all memory images for all users. It must provide direct access to these memory images. Then rollout roll-in swapping variant used for priority-based scheduling algorithm. Lower priority process is swapped out, so higher priority processes can be loaded and executed. The major part of swap time is transfer time. Total transfer time is directly proportional to the amount of memory swapped. The modified versions of swapping are found on many operating systems such as Unix, Linux, and Windows. So this is swapping. This is our hard disk. This is our RAM. So when suppose process P2 is going to be having higher priority, then we need to remove process P1 from the main memory. So we are going to remove P1 from, that is called as swap out, and this process is called as swapping. This hard disk is called as backing store. So how it is process P1, P2. P1 goes for I input output wait, then it is going to be swapped out. Instead of again P3 processor is swap in. Then P1 comes back after IO, then again P3 is taken out, again P1 is. So in this way, the processors can execute multiple processes simultaneously. So it will become multi-processing environment, and that will overall speed up the quality of the execution time for all the processes. So if a process is waiting for some resources, or it may having a low priority than the incoming request process, then it will be swapped out. And when its execution is needed, or when the request is satisfied, when that request is going to be satisfied, it is going to right. So this is about swapping. Now we'll go to the memory consistency models. So what is memory consistency? We have small example. Suppose this is process P1 and this is process P2. Let us have two different processes, and this is, sorry, and this is my memory. Here I have stored A value 10 and B value 50. Both process P1 and P2 access the main memory. Inside this, these are going to have a process space for themselves. So both will store A, B equals to whatever the value in the main memory. Are you getting this? So the earlier values are 10 and 50. Now what will happen is P1 will change A value to A plus B. Then new value of A will be how much? Can anyone tell me? New value of A will be how much? A is 10 and B is 15. P1 executes A equal to A plus B. What is A's new value? 25. Then it has stored 25, but in the system it is only 10. So what will happen is, if it is P2 later wants to calculate on B, suppose it wants to perform B equals to A minus B, it will return in minus 5, but whereas it should return 10. Why it is happening? Because whatever updated here is not reflecting in the main memory. This is the problem. So how it can be solved is using cache coherency. So there are two mechanisms. One is write back and the other one is write through. We have studied this. Write through means whenever you are going to update, the same is going to be updated in the main memory also. Whereas write back is when the process execution is going to be over, then when you are going to replace the block to the main memory, at that time it is going to be changed. Now what will happen is intuition says load should return latest value. Then what is meant by latest? Coherence concerns only about one memory location. Whatever we have discussed is only about for A. Whereas consistency concerns about apparent ordering for all locations. A memory system is coherent if for all locations can serialize all operations to that location such that operations performed by one processor appear in program order. Then what is program order? To order defined by a program text or assembly code, a read gets the value written by last store to that location. This is about coherency. Then, what is consistency? Consistency, it is a contract between the system and the programmer. It defines the correct behavior. Then, coherence protocol is only a means to an end. Coherence is not visible to software. Coherence is not visible to, sorry. It enables a new system to present same consistency model despite using newer, fancier coherence protocol. Consistency model restricts ordering of loads and stores. It does not care all about ordering of the coherence messages. For example, we'll show. Suppose A1, B1 and flag. If A equal to B equal to flag equals to 0, it is P2 is waiting. But when P1 changes to this, it should print. It occurs only when it should print A and B. Yet in some consistency model, this is int required because it will go on spinning because the new value of flag is not updated here and hence it goes on spinning. Coherence doesn't say anything because coherence is only concerned about storing this into this. It doesn't tell about whether that updated version to be brought to the other processes. Then we, in order to solve this, we have come across different consistency models. In that we are going to introduce what is meant by consistency in that sequential consistency. A multiprocessor is sequentially consistent if the result of any execution is the same as if the operations of all the processors were executed in some sequential order and the operations of each individual processor appear in this sequence in the order specified by its program. It is nothing but a multitasking uniprocessor. If the order of execution is just like a uniprocessor, then we can tell that it has achieved sequential consistency. The memory model is sequential processors issue memory operations in program order P1, P2 up to Pn. So randomly set after each memory operation, it will be doing. This is called as a memory model. In the next class, we are going to look about in detail. Sequentially consistent execution result is same as one of the possible interleavings on uniprocessor. Sequentially consisting system is any possible execution correspond to some possible total order. Alternate equivalent definition of sequential consistency is there exists a total order of all loads and stores such that the value returned by each load equals the value of the most recent store to that location. So in this class, we have learned about structure of interleaved memory organization, difference between coherency and consistency, and the important questions are explain the difference between cache coherence and cache consistency. Explain different memory allocation schemes. You need to explain both contiguous, non-contiguous, then static as well as dynamic algorithms. So this is taken from Kai Hong and Naresh Jotwani book, section 5.3.3 to 5.3.4. With this, I am going to conclude the chapter. Is there any doubts?